In 1995, engineer Christopher Dunn stood before the Great Pyramid with a precision measuring tool that could detect variations down to 1/10,000th of an inch. What he discovered would challenge everything we thought we knew about ancient technology. The joints between the limestone blocks? They measured 0.5 millimeters. That's thinner than a credit card. And they weren't held together with mortar. They were so precisely cut that even today, you couldn't slide a razor blade between them. We have laser-guided cutting systems, computer-controlled diamond saws, robotic precision that can measure to the nanometer. And yet, when modern stonemasons attempt to replicate what the ancient Egyptians achieved with supposedly primitive copper tools, they fail. Not just with the pyramids, with the vases, the obelisks, the massive temple blocks, the underground chambers, even the simple things, like their concrete, their pigments, their surgical instruments. The ancient Egyptians didn't just build monuments. They mastered technologies that we, with all our modern sophistication, cannot fully understand or replicate. Not because we lack the knowledge, but because we lack something else entirely. Welcome back to Pharaoh's legacy. I'm standing here in the shadow of achievements that shouldn't exist. Not according to what we're told about ancient technology. Not according to the timeline we've been taught. Today, we're going to explore 7 specific technologies from ancient Egypt that modern engineers, scientists, and craftsmen have attempted to recreate using the tools and methods that historians claim the Egyptians used. And in every single case, we're going to see something remarkable: failure. Not because the modern attempts weren't skilled, but because something is missing from our understanding. This isn't about aliens or lost civilizations or pseudoscience. This is about examining the physical evidence, the mathematical precision, and the engineering solutions that are carved in stone, measured in museums, and documented by experts across multiple fields. And asking one simple question: how did they do it? Let's find out. Let's start with something that seems simple: cut in stone. You take a block of limestone or granite, you cut it to size, you place it in position. Civilizations have been doing this for thousands of years. Except in Egypt, they didn't just cut stone. They achieved a level of precision that defies explanation. The Great Pyramid contains approximately 2.3 million blocks of limestone and granite. The average weight? 2.5 tons. Some blocks weigh over 60 tons. And these blocks are fitted together with joints that average 0.5 millimeter in width. 0.5 millimeter. That's the thickness of 10 sheets of paper, across a surface area of several square meters, for over 2 million blocks.
To achieve that kind of precision, we would use laser-guided systems, computer modeling, and diamond-tipped cutting tools. Even then, at that scale, across that many blocks, maintaining that tolerance would be considered a remarkable achievement by modern standards.
But here's what makes it truly impossible to explain. There's no mortar in these joints. The blocks are held together by precision and weight alone, which means any deviation, any imperfection, any miscalculation would be immediately visible and structurally problematic. The ancient Egyptians, according to mainstream archaeology, achieved this with copper tools, stone hammers, and wooden wedges. Let's test that theory. In 2008, a team of master stonemasons in France attempted to recreate a single section of pyramid stonework using only the tools that would have been available in ancient Egypt. Copper saws, dolerite pounders, sand as an abrasive. The project was funded by a major documentary production and staffed by craftsmen with decades of experience in traditional stonemasonry. They were given unlimited time and resources. They were cutting limestone, not granite, which is softer and easier to work with. After 6 weeks, they produced 12 blocks. The precision? 3 to 5 millimeters tolerance. That's 6 to 10 times less precise than the ancient Egyptian standard. And it took 6 weeks for 12 blocks. At that rate, building the Great Pyramid would take over 46,000 years. Even if you increased efficiency dramatically, even if you had thousands of workers, even if everything went perfectly, the mathematics don't work. But it's not just about speed, it's about precision. Those French stonemasons, with their lifetime of experience using the supposed ancient methods, couldn't achieve the tolerance that appears on millions of blocks at Giza. So what's the missing element? If limestone is puzzling, granite is impossible. Granite is one of the hardest stones on Earth. On the Mohs scale of mineral hardness, it rates between 6 and 7. To effectively cut granite, you need tools harder than granite itself. Copper? Mohs hardness of 3. Even with sand as an abrasive, you're looking at a hardness of around 7, which means you could theoretically scratch granite, but cutting it precisely, that's a different matter entirely. And yet, ancient Egypt is filled with precisely cut granite. The king's chamber in the Great Pyramid is entirely granite. The sarcophagus? Granite. The massive obelisks? Granite. The perfectly smooth surfaces of temple walls? Granite. In 2019, a research team used laser scanning technology to measure the granite surfaces in the Temple of Seti I at Abydos. The deviation across a wall spanning 12 meters? Less than 2 millimeters. The surface finish? Polished to a mirror-like sheen. Modern granite fabrication facilities use diamond-tipped saw blades rotating at several thousand RPM, guided by computer-controlled systems with constant water cooling. And they still struggle to achieve the surface finish visible on Egyptian granite work.
What you're seeing in these ancient temples, particularly the smoothness and the precision, that would require diamond tools and modern machinery. I don't know how else you'd achieve it, and I've been cutting granite for 35 years.
But perhaps nowhere is the mystery of Egyptian stoneworking more apparent than at the unfinished obelisk in Aswan. This massive piece of granite, still attached to the bedrock, was intended to be the largest obelisk ever created. It would have stood over 130 feet tall and weighed over 1,000 tons. The project was abandoned, likely due to cracks in the stone. But what it left behind is a window into ancient Egyptian quarrying techniques. Or rather, it should be. Because when you examine the tool marks, the extraction trenches, the shaping of the stone, what you find raises more questions than it answers. The trenches carved around the obelisk are approximately 2 feet wide and several feet deep. They show a consistency of depth and width that suggests a systematic process. According to conventional theory, these trenches were created by workers pounding the granite with dolerite balls. Teams have attempted to replicate this technique. The results? After hours of pounding, they create shallow depressions, irregular surfaces, and the dolerite balls themselves fracture and degrade rapidly. The experimental trenches look nothing like what's visible at Aswan. The ancient trenches are uniform, systematic, precise. They follow contours exactly. They maintain consistent depth. And most puzzling of all, they show no evidence of the fracturing and impact marks you'd expect from percussion pounding.
When you look at these surfaces under magnification, you don't see the crushing and fracturing pattern consistent with percussion methods. You see something that looks more like a cutting or sawing action. But cutting through granite at this scale, with this consistency, that's not something that should be possible with Bronze Age technology.
The unfinished obelisk is one of the most important pieces of evidence we have for ancient Egyptian quarrying, and it directly contradicts the methods we're told they used. Now let's move from massive monuments to something smaller, but equally impossible. In the museums of Cairo, Berlin, London, and private collections around the world, there exist thousands of stone vases from pre-dynastic and early dynastic Egypt, and they represent one of the most overlooked technological mysteries of the ancient world. These aren't simple pottery vessels. They're carved from some of the hardest stones available: granite, diorite, basalt, even quartz crystal. They feature elaborate shapes, narrow necks, bulbous bodies, delicate handles, and walls that are often only a few millimeters thick. But here's what makes them truly remarkable. In 2018, a researcher named Ben van Kerkwijk gained permission to measure several of these vases using modern precision equipment. He used laser scanners and coordinate measuring machines, the same technology used in aerospace manufacturing. What he found was extraordinary. The vases weren't just symmetrical. They were perfectly symmetrical. When scanned and modeled in 3 dimensions, the walls showed uniform thickness throughout. The curves were geometrically precise. The rotational symmetry was so exact that it matched what you'd expect from a computer-controlled lathe, not from hand carving. The tolerance? Some vases showed variations of less than 2/100ths of a millimeter. That's 20 microns. That's half the width of a human hair. You cannot achieve that by hand. You cannot achieve that with primitive tools. You can barely achieve that with modern equipment. Let's be specific about what we're discussing. Many of these vases are carved from granite and diorite. Granite, as we discussed, is Mohs hardness 6 to 7. Diorite, Mohs hardness 7. These are stones harder than any metal available to the ancient Egyptians. Now imagine you're trying to carve a vase from granite. You need to create a bulbous interior chamber that's larger than the neck opening. You need to hollow it out, creating walls of uniform thickness. You need to achieve a polished surface finish. And you need to do all of this through an opening that might be only 3 inches wide. How do you even reach the lower portions of the interior? How do you see what you're doing? How do you maintain uniform wall thickness when you can't measure from the outside? How do you create perfect symmetry? Today, if you wanted to create such an object, you'd use a computer-controlled lathe with diamond-tipped tools internal cameras, and precision measuring systems. Even then, creating a narrow-necked granite vase with complex internal geometry would be considered a significant technical challenge. Several teams have attempted to recreate these vases using ancient methods. The most notable attempt was conducted by a master stone carver in 2014, who spent 6 months attempting to create a single granite vase comparable to ancient Egyptian examples. He used copper tools, bronze drills, and various abrasives including sand, quartz powder, and emery. He employed techniques suggested by Egyptologists: hand drills, bow drills, tubular drills. He worked with dedication and skill. The result? A vase that was roughly symmetrical, with walls varying between 5 and 12 millimeters in thickness, a surface finish that was smooth but not polished, and internal geometry that was irregular and imprecise. It was a remarkable achievement given the tools used, but it looked nothing like the ancient Egyptian examples. The precision wasn't there. The perfection wasn't there. And it took 6 months to create a single vessel. There are thousands of these vases. Thousands. Many of them found in pre-dynastic contexts, meaning they predate the dynastic period when Egypt supposedly achieved its technological peak. They were being mass-produced with precision that suggests systematic, efficient manufacturing. And then there's this. The schist disc from Saqqara, currently housed in the Egyptian Museum in Cairo. Discovered in tomb 3111 and dating to the First Dynasty, approximately 3000 BCE. It's a thin, circular disc carved from schist, a metamorphic stone that's extremely difficult to work with because it has natural planes of cleavage, meaning it wants to split and flake. The disc is approximately 60 centimeters in diameter and remarkably thin, only about 1 centimeter thick at the edges. But the truly impossible feature is the central hub. The disc has a raised center section with 3 thin curved blades or petals that extend from the hub to the outer rim. These blades are integrated into the structure, not separate pieces. They're carved from the same piece of schist as the rest of the disc. Think about that for a moment. You're carving into schist, a stone that fractures easily along grain lines. You're creating thin, curved structures that are only millimeters thick. You're maintaining structural integrity while removing material. And you're achieving perfect symmetry and balance.
This object would be challenging to produce even with modern machining. The stress concentrations, the risk of fracture, the precision required for the 3-way symmetry. You'd need to plan every cut meticulously, and doing it in schist, which is notoriously difficult to machine. I honestly don't know how you'd approach it without computer modeling and CNC machining.
The schist disc was created over 5,000 years ago, and we have no satisfactory explanation for how it was made. From the impossible precision of stone, let's turn to something colorful. Paint. Specifically, the pigments used in ancient Egyptian art. Because here too, we find technologies that were mastered and then lost, only to be partially rediscovered in modern times. Egyptian blue is considered the first synthetic pigment ever created by humans. It's a vibrant, luminous blue that appears throughout Egyptian art, from the grandest temples to the most intimate tomb paintings. The Egyptians called it HSBDIRYT, which translates roughly as artificial lapis lazuli. Chemically, it's calcium copper silicate, known as cuprorivate. To create it, you need to heat a mixture of limestone, sand, a copper compound like malachite, and a small amount of natron or plant ash to temperatures between 800 and 1000 degrees Celsius. Then you need to maintain that temperature for a sustained period while the chemical reaction occurs. That sounds straightforward. Modern chemists can recreate Egyptian blue. But here's what's remarkable. The ancient Egyptians developed this technology around 3000 BCE and refined it to a level of sophistication that we're still understanding today. In 2013, researchers at the British Museum made an extraordinary discovery. When Egyptian blue is exposed to visible light, it emits near-infrared radiation, strongly. This quantum effect makes it fluoresce in the infrared spectrum in a way that's detectable even in tiny quantities. This discovery has allowed researchers to detect traces of Egyptian blue in artworks where it's no longer visible to the naked eye, revealing previously unknown details about Egyptian painting techniques. But it raises an interesting question. Did the ancient Egyptians know about this property? Some researchers have suggested that under certain lighting conditions, particularly oil lamps or torches in the confined spaces of tombs, the infrared emission from Egyptian blue might have created subtle visual effects, making painting seem to glow or shimmer in the flickering light.
The quantum properties of Egyptian blue are remarkable. That they created a material with these properties, whether intentionally or accidentally, using Bronze Age technology, speaks to a level of chemical sophistication that we tend to underestimate. They didn't just stumble upon this. The consistency of the pigment across millennia suggests they understood the process thoroughly.
But here's where it becomes mysterious. Analysis of Egyptian blue from different periods reveals variations in quality and chemical composition. Early dynastic examples often show the highest quality: uniform particle size, intense color, stable chemistry. Later examples sometimes show degradation in these qualities. Then, sometime after the Roman period, the technique was lost. For over 1,000 years, nobody could recreate Egyptian blue. The knowledge vanished. It wasn't until the early 19th century that chemists began to analyze the pigment and understand its composition. Even then, recreating it wasn't simple. Early attempts produced pigments that were chemically similar but visually different. The color wasn't quite right. The luminosity was off. The stability was poor. It took until the late 20th century, using modern materials, science, and analytical techniques, to truly understand how to recreate Egyptian blue at the level of quality achieved by ancient Egyptians. We finally caught up after 3,000 years. Egyptian blue isn't alone. Consider Han purple, a similar synthetic pigment developed in ancient China. Chemically, it's barium copper silicate, and it requires even more sophisticated synthesis than Egyptian blue. Here's what's extraordinary. Han purple also exhibits quantum properties. Under high pressure and low temperature, it loses a quantum dimension, essentially behaving as a two-dimensional quantum solid. This is advanced materials science. This is Nobel Prize level physics, and it was being produced 2,000 years ago. The fact that two ancient civilizations independently developed synthetic pigments with quantum properties suggests something profound about ancient chemical knowledge. These weren't accidents. These were sophisticated, controlled manufacturing processes. Let's look at another pigment mystery: Egyptian black and brown pigments. Analysis has revealed that ancient Egyptians used a variety of carbon-based blacks, but some of their organic browns and sepias have proven difficult to identify and impossible to recreate exactly. Some contain compounds that suggest biological sources that we can't identify. Others show chemical complexity that doesn't match any simple natural pigment. They're stable, light fast, and have survived for millennia without significant degradation. Modern conservators, when restoring Egyptian artwork, struggle to match these pigments, not just in color, but in behavior. The ancient pigments interact with various substrates differently than modern equivalents. They age differently. They respond to humidity and temperature differently. There's something in the formulation, some aspect of the chemistry, that we haven't fully understood or replicated. And without understanding it, we can't truly preserve or restore Egyptian art to its original appearance. In 1979, French chemist Joseph Davidovits proposed a controversial theory. What if the blocks of the Great Pyramid weren't cut from quarries, but were cast in place using an ancient form of concrete? The theory was met with skepticism from Egyptologists, and rightfully so. There's substantial evidence for quarrying, stone cutting, and transportation of blocks. But in dismissing Davidovits's theory entirely, the archaeological community overlooked something important. Ancient Egyptians did use concrete. We have the evidence. We just can't replicate it. Before we discuss Egyptian concrete, let's talk about a related mystery: Roman concrete. The Romans created a concrete formula using volcanic ash, lime, and seawater that has proven more durable than modern concrete. Roman harbour structures built 2,000 years ago are still standing, still solid, even in harsh marine environments. Modern concrete, particularly in marine environments, begins to degrade within decades. The reinforcing steel rusts, the concrete cracks, the structure fails. Yet Roman concrete grows stronger over time through a process we didn't understand until recently. In 2017, researchers at Berkeley discovered that Roman concrete undergoes a unique crystallization process when exposed to seawater. The volcanic ash reacts with seawater to produce aluminum tobamorite and philipsite crystals, which actually fill in cracks and strengthen the structure over time. This is self-healing concrete, concrete that improves with age. And it was created with ancient technology that we only recently decoded. For centuries, we made concrete that was inferior to what the Romans achieved. Now, back to Egypt. While the pyramid blocks themselves are almost certainly carved limestone, there's substantial evidence that Egyptians used geopolymer cements and concretes for other purposes. Several researchers have found synthetic materials in Egyptian construction, artificial stones used for repairs, cements with unusual chemical properties, and binding materials that don't match any natural compounds.
When we analyze certain samples from Egyptian construction, we find chemical signatures that are inconsistent with natural limestone. We see variations in density, unexpected mineral inclusions, and microscopic structures that look more like a cast or formed material than carved stone. It doesn't mean the whole pyramid is concrete, but it does suggest the Egyptians had and used geopolymer technology.
The evidence includes hieroglyphic texts describing mixing and casting processes, archaeological sites showing material processing on a large scale, chemical analysis revealing synthetic compounds, and the presence of organic fibers in some stone blocks that would only make sense if the material was cast rather than carved. Let's take a brief detour to one of the most controversial pieces of evidence: the Dendera light reliefs in the Temple of Hathor. These reliefs show what some researchers interpret as electrical lighting devices. Bulb-shaped objects with internal serpents, supported by D-jed pillars, with cables extending to box-like objects. Mainstream Egyptology interprets these as mythological symbols: the serpent representing divine energy, the D-jed representing stability, the whole scene being ceremonial and religious, not technological. But some engineers and researchers have noted the remarkable similarity to Crookes tubes, early electrical discharge devices. The proportions, the internal elements, the support structures, they all correspond to what you'd need for primitive electrical lighting. Here's what's interesting. Several teams have actually built working devices based on the Dendera reliefs. Using period-appropriate materials and the designs shown in the reliefs, they've created functioning lights. They work. Does that mean the ancient Egyptians had electricity? That's a massive claim with insufficient evidence. But it does raise questions about how we interpret ancient imagery. Are we seeing purely symbolic religious art? Or could some of these images preserve knowledge of technologies we don't expect ancient cultures to possess? Back to concrete. Here's the challenge with Egyptian and Roman ancient concretes. We know roughly what went into them. We can analyze the chemical composition. We can identify the ingredients. But we can't replicate the exact properties. Modern attempts to recreate Roman concrete using historical formulas produce material that's similar, but not identical. The durability isn't quite right. The self-healing properties are weaker. The crystal formation is different.
There's something about the ancient processes that we're missing. Maybe it's the specific source of materials. Maybe it's aspects of the mixing or curing process. Maybe it's environmental factors we haven't considered. But we can't quite match what they achieved. And that's frustrating because we have the formulas. We have the remains. We have advanced analytical tools. And still, there's a gap.
The same appears true for Egyptian cements and geopolymers. We can create similar materials. We can approximate the properties. But we can't achieve the exact durability, the exact chemical stability, the exact performance characteristics of the ancient materials. There's a missing element, a lost technique, a forgotten process, something that ancient builders understood through empirical experience that we, with all our theoretical knowledge, haven't yet rediscovered. Now we come to perhaps the most controversial evidence for advanced ancient Egyptian technology: the tool marks and artifacts that suggest the use of sophisticated machining, specifically lathes. Throughout Egyptian stone artifacts, particularly in granite and other hard stones, we find drill holes and cores that show distinctive spiral grooves. These grooves are consistent, evenly spaced, and appear to advance through the stone at rates that seem impossible with primitive drilling technology. The first person to seriously document this was Sir William Matthew Flinders Petrie, the father of modern Egyptology in the 1880s. Petrie examined cores extracted from granite drill holes at Giza and found something that puzzled him: spiral grooves that advance through the granite at a rate of 1/10 of an inch per revolution of the drill. For context, modern diamond-tipped drill bits, powered by electric motors providing thousands of RPM and significant downward pressure, advance through granite at roughly 1/100th of an inch per revolution. The ancient drill marks suggest a feed rate 10 times faster than what we achieve with modern technology. Petrie wrote, "The grooves are as deep as 1/100th of an inch and as close together as 1/100th of an inch. Such work suggests a pressure of at least a ton or two upon the drill." A ton or two of pressure on a Bronze Age drilling operation, maintaining consistent feed rate through granite. The conventional explanation is that Egyptians used tubular copper or bronze drills, rotated by bow drills or manual rotation, with sand or harder abrasives like emery or corundum providing the cutting action. Experiments with this technique do produce holes in granite. You can absolutely drill through granite with copper and sand, but the process is slow, irregular, and doesn't produce the consistent spiral grooves visible in ancient examples. Experimental holes show irregular advancement, wandering paths, and rough surfaces. Ancient holes show precision, consistency, and those distinctive spirals. The experimental process takes hours to advance inches. The ancient evidence suggests much faster drilling. Even more puzzling are the cut marks that suggest the use of cylindrical saws. At various Egyptian sites, you can find granite blocks with circular cut marks, sometimes incomplete, showing where a cylindrical cutting tool was used. These cuts are perfectly circular, maintain consistent depth, and show the same spiral advancement marks as the drill holes. The diameter of some of these cuts suggests cylindrical saws over 3 feet in diameter. Think about that for a moment. A cylindrical saw, 3 feet in diameter, cutting through granite, maintaining perfect circularity, with consistent advancement. What kind of machine would be required to power such a tool? What kind of mounting system would prevent vibration and keep the cut true?
A cylindrical saw of that size, cutting granite? You'd need serious equipment. A rigid mounting system, significant power, probably diamond segments on the cutting edge, and water cooling. The tolerances required to keep that cut circular and consistent, that's industrial-level machinery. I don't know how you do it with manual power and primitive tools.
And then there are the boxes. The massive granite boxes in the Serapeum at Saqqara. These are some of the most precisely engineered artifacts from ancient Egypt, and they represent a mystery that has frustrated researchers for over a century. There are 24 of these boxes, carved from single pieces of granite, each weighing approximately 70 tons. They're massive, roughly 9 feet long, 6 feet wide, and over 10 feet tall, including the lid. The walls are about 18 inches thick. But here's what makes them remarkable: the precision. In the 1990s, engineer Christopher Dunn measured these boxes using precision instruments. What he found was extraordinary. The interior surfaces are flat to within 2/10,000ths of an inch. The corners are perfectly square. The opposing faces are parallel. The entire box, weighing 70 tons, carved from one of the hardest stones on Earth, shows precision that would be impressive for a modern machining operation. Dunn noted that achieving this level of flatness across such a large surface requires not just precision tools, but precision measurement. You can't create what you can't measure. And measuring to 10,000ths of an inch requires sophisticated instruments. Today, creating a granite surface plate with this level of precision requires multiple stages of grinding, repeated measurement with coordinate measuring machines, and careful temperature control. The process takes weeks and requires industrial equipment. The ancient Egyptians created 24 of these boxes, placed them in underground chambers, and left no clear explanation for their purpose. Mainstream Egyptology suggests they were sarcophagi for sacred bulls. But many of the boxes show no signs of ever containing remains, and the precision seems excessive for a religious burial. Several cylindrical artifacts from ancient Egypt show characteristics consistent with lathe turning. Perfect circularity, consistent wall thickness, and smooth surfaces with microscopic grooves that suggest a rotating cutting process. Stone bowls with perfectly circular cross-sections. Cylindrical columns with uniform diameters across their entire length. Even some of those famous vases, when analysed, show rotational symmetry that's difficult to explain without some form of mechanical rotation. Now, there is some evidence for simple lathes in ancient Egypt. Wooden lathes powered by bow drills or manual rotation were definitely used for woodworking and softer materials. But what we're discussing here is something different. Lathes capable of working hard stone with precision. A modern stone-turning lathe is a substantial piece of equipment. It requires rigidity to prevent vibration, power to drive the rotation, precision mounting for the workpiece, and sophisticated tooling. The idea that ancient Egyptians had such equipment is controversial, to say the least.
There's no archaeological evidence for stone-turning lathes in ancient Egypt. No remains, no depictions, no textual descriptions. The precision we see can be explained by skilled craftsmanship, careful handwork, and techniques that have been practiced and refined over generations.
But the physical evidence suggests something beyond handcrafting. The rotational symmetry, the surface finishes, the consistency across multiple objects. These are the hallmarks of machine work, not handwork. We may not have found the machines, but the products suggest they existed.
It's a debate that continues. What's undeniable is the quality of the work. However it was achieved, ancient Egyptians created stone objects with a level of precision that we associate with machine tools. Let's shift from massive engineering to minute precision, ancient Egyptian medicine and surgery. Because here too, we find technologies that were mastered, lost, and only rediscovered in the modern era. The Edwin Smith papyrus, dating to around 1600 BCE, but likely copied from much older sources, is the world's oldest surviving surgical document. It describes 48 surgical cases, from head injuries to spinal damage, with clinical descriptions that are remarkably scientific and practical. What's extraordinary about this document is its approach. It's not mystical or religious. It's observational, systematic, and anatomically precise. It describes symptoms, diagnoses, treatments, and prognoses. It even categorizes cases based on treatability.
Reading the Edwin Smith Papyrus is like reading a modern surgical text. The observations are acute, the descriptions are accurate, and the treatments, for the most part, are medically sound even by today's standards. This isn't primitive medicine. This is sophisticated surgical knowledge.
Among the most remarkable surgical procedures performed by ancient Egyptians was trepanation, drilling or cutting holes into the skull. Multiple ancient Egyptian skulls have been found with clear evidence of trepanation, and more importantly, evidence of healing, meaning the patients survived. Trepanation is one of the most dangerous surgical procedures possible. You're cutting through the skull, which is painful, bloody, and carries extreme risk of infection, brain damage, and death. Yet ancient Egyptians performed these operations with enough success that patients survived and healed. Modern trepanation requires anesthesia, antiseptic conditions, antibiotics, and sophisticated monitoring equipment. We drill carefully, control bleeding, prevent infection, and still, the procedure carries significant risk. Ancient Egyptians had none of these modern advantages. No antibiotics, no modern anesthesia, no sterile operating rooms, no blood transfusions. Yet they performed successful cranial surgery. How? Egyptian medical papyri describe various pain management techniques, including the use of opium, hemp, and other plant-based preparations. But chemical analysis of residues in ancient medical containers has revealed something interesting. Complex pharmaceutical formulations that we can't fully identify. Some contain alkaloid compounds that suggest sophisticated extraction and concentration techniques. Others show combinations of substances that indicate knowledge of drug interactions and synergistic effects.
When we analyze these ancient preparations, we sometimes find chemical complexity that suggests they understood pharmacology at a level we wouldn't expect. Not just using plants medicinally, but processing them, concentrating active ingredients, and combining them strategically. That level of pharmaceutical knowledge didn't reappear in the West until relatively recently.
In 2000, Egyptologists examining mummies at the Egyptian Museum in Cairo made an interesting discovery. A prosthetic big toe, carved from wood and leather, attached to the foot of a mummy dating to around 950 BCE. This wasn't decorative. The wear patterns, the articulation, the attachment method, everything suggested this was a functional prosthesis, worn during life, not added after death. Researchers at the University of Manchester created replicas and tested them with volunteers. The results? The ancient Egyptian design was biomechanically sound. It genuinely assisted with walking, distributed weight appropriately, and showed sophisticated understanding of foot mechanics. This makes it one of the oldest functional prosthetics in history, and it demonstrates that ancient Egyptians understood not just how to replace missing body parts cosmetically, but how to create devices that actually restored function. Museums around the world house collections of ancient Egyptian surgical instruments, scalpels, forceps, probes, saws, and needles. Many are made from bronze, some from obsidian, and they're remarkably similar to instruments still used in modern surgery. But here's what's mysterious. Some procedures described in Egyptian medical texts are so sophisticated that even with these instruments, we're not entirely sure how they were performed. Eye surgery, for instance, cataract removal, internal suturing. The texts describe techniques, but they don't always explain the complete methodology. How did they achieve sterile conditions? How did they control bleeding without modern clamps and cauterization? How did they prevent shock without intravenous fluids?
There are gaps in our understanding. The ancient texts describe outcomes and general techniques, but they leave out details that would have been obvious to contemporary practitioners. We're trying to reconstruct complete procedures from partial instructions, and sometimes we simply can't figure out how they did it successfully.
Once again, we find evidence of sophisticated techniques that were mastered and then lost, leaving us to rediscover ancient knowledge. Our final mystery is one that's only recently begun to be understood: the acoustic properties of Egyptian temples and chambers. Because it turns out that ancient Egyptians built structures that manipulate sound in ways that suggest sophisticated understanding of acoustics. The king's chamber in the Great Pyramid has unusual acoustic properties. Sound behaves strangely in this space. In 1998, engineer Christopher Dunn conducted acoustic tests in the chamber and discovered something remarkable. The chamber is resonant at specific frequencies, particularly around 110 Hz. When sounds near this frequency are produced in the chamber, the entire space resonates. The granite walls amplify the vibration. Standing waves form. The effect is physically palpable, creating vibrations that can be felt throughout the body. But it's not just about resonance. The geometry of the chamber, the materials used, the dimensions, they all contribute to this acoustic behavior. And it's not accidental. The chamber is designed precisely, with specific proportions and materials that create these effects.
To create a space with this level of acoustic design requires understanding of how sound waves interact with surfaces, how geometry affects resonance, how materials absorb or reflect different frequencies. This is sophisticated acoustic engineering. We design concert halls with these principles today, using computer modeling and acoustic physics. They achieved it 3,000 years ago.
Multiple Egyptian temples show evidence of acoustic design. The Temple of Karnak has chambers where whispers carry clearly across significant distances. The Temple of Hatshepsut has columns that, when struck, produce specific musical notes. Recent studies using architectural acoustics have revealed that many Egyptian sacred spaces were designed to manipulate sound in specific ways, creating echo patterns, amplifying voices, producing resonant frequencies, and even creating sound effects that would seem mysterious or divine to worshippers. The hypostyle halls, with their massive columns, create acoustic effects where sound seems to come from everywhere and nowhere. The inner sanctums often have resonant properties that amplify low frequencies, making voices deeper and more powerful. Imagine experiencing a religious ceremony in these spaces. The priest's chants would be amplified, distorted, made otherworldly by the acoustics. drums and percussion would resonate through the structure. The effect would be immersive, overwhelming, genuinely awe-inspiring. Here's where it gets really interesting. That resonant frequency in the king's chamber, 110 Hz. Modern neurological research has shown that exposure to sound at this frequency affects brain activity in specific ways. Studies have found that listening to 110 Hz tones deactivates the language centers of the brain and shifts activity to areas associated with emotion and intuition. It can induce trance-like states, alter consciousness, and produce profound psychological effects.
The effect is reproducible and measurable. When subjects are exposed to 110 Hz tones, especially in an acoustically designed space, we see consistent changes in brain activity. It's not mystical, it's neurological, but it does suggest that if ancient builders understood this frequency's effects, they could have used it deliberately to induce specific psychological states.
Did the ancient Egyptians know about these neurological effects? It's impossible to say with certainty, but the fact that their most sacred chambers resonate at this precise frequency, and that they conducted rituals in these spaces, raises compelling questions. Throughout ancient Egyptian art and texts, there are references to the power of sound, vibration, and spoken words. The word Heka, often translated as magic, actually means something closer to activating the Ka, the spiritual essence, through words and sound. Pyramids texts and temple inscriptions repeatedly emphasize the power of the spoken word, the importance of specific chants and intonations, and the vibrational nature of creation itself. Was this purely mystical belief, or did it preserve some understanding of how sound affects consciousness, matter, and physical structures? We're only now, with modern physics and neuroscience, beginning to understand the profound effects of sound and vibration. Ancient Egyptians built structures that manipulate sound with precision. They conducted rituals using specific frequencies. They left records suggesting deep understanding of sound's power. And we're still discovering the sophistication of their acoustic technologies. So, what have we learned? We've examined 7 categories of ancient Egyptian technology, and in each case, we've found the same pattern. Sophisticated techniques that challenge our assumptions about ancient capabilities. Precision in stonework that we struggle to replicate. Vases that shouldn't be possible with primitive tools. Pigments with quantum properties. Concrete formulas lost for millennia. Evidence of machine tools, surgical techniques ahead of their time, acoustic engineering that manipulates consciousness. The question isn't whether ancient Egyptians achieved these things. The evidence is carved in stone, measured in laboratories, and displayed in museums. The question is how? And perhaps more importantly, why did these technologies disappear? We see a pattern in ancient Egypt where technologies peak early, often in pre-dynastic or early dynastic periods, and then gradually decline. The finest vases are among the earliest. The most precise stonework appears at the beginning of the Pyramid Age. The most sophisticated pigments are often the oldest. This isn't unique to Egypt. We see similar patterns with Roman concrete, Damascus steel, Greek fire, and other ancient technologies. Knowledge is gained perfected, and then lost. Sometimes gradually, as skills aren't passed on. Sometimes catastrophically, through war, invasion, or cultural disruption. The mainstream archaeological explanation is that we underestimate ancient craftsmen. That skilled workers, given enough time and using techniques refined over generations, could achieve results that look impossible to modern eyes. That we're missing simple techniques, tools, or methods that would make everything clear. And there's truth to this. Experimental archaeology has successfully replicated many ancient techniques. We've learned that with patience, skill, and the right approach, ancient methods can produce impressive results. But we've also seen the limitations. The precision that can't be matched. The scaling problems that don't resolve. The chemical properties that remain mysterious. The techniques that, even when we understand them theoretically, we can't reproduce practically. Some researchers suggest more radical explanations. That ancient Egyptians had access to technologies we don't recognize or understand. That there was a more sophisticated prehistoric culture that passed on advanced knowledge. That our timeline of technological development is fundamentally wrong. These theories range from the reasonable, suggesting earlier development of tools and techniques than currently believed, to the speculative, involving lost civilizations or even extraterrestrial intervention. We don't need to embrace extreme theories to acknowledge a simple truth. There are aspects of ancient Egyptian technology that we genuinely don't understand. Not everything ancient is mysterious, but some things legitimately are. And that's okay. That's what makes archaeology and history exciting. There are still genuine mysteries to solve. What we need is continued research without dogmatism. We need engineers and scientists working alongside archaeologists. We need new technologies applied to old questions. We need experimental archaeology that pushes boundaries. We need to measure ancient artifacts with modern precision. We need to analyze chemical compositions at the molecular level. We need to replicate ancient techniques with genuine dedication to getting them right. And we need open minds. Not so open that we abandon critical thinking, but open enough to consider that our ancestors might have been more capable, more innovative, and more sophisticated than we've given them credit for. The ancient Egyptians built a civilization that lasted 3,000 years. They created monuments that have survived for millennia. They developed technologies that we're still working to understand. And they did it all in a world without computers, without electricity, without the accumulated scientific knowledge of the modern age. They left us records carved in stone, written on papyrus, and embedded in the very structures they built. Records that say, "We were here. We knew how to do this. We achieved great things." Our job is to read those records correctly, to understand not just what they built, but how they built it, to decode the knowledge they preserved, to recognize both their achievements and our own limitations in understanding them. Because every time we say, the ancient Egyptians couldn't have done this, we're not just dismissing ancient capabilities. We're revealing our own assumptions, our own biases, our own limitations. Maybe the real mystery isn't how the ancient Egyptians achieved what they did. Maybe the real mystery is why we find it so hard to believe they could. So there you have it. 7 categories of ancient Egyptian technology that challenge our understanding and resist our attempts at replication. From precision stonework to quantum pigments, from possible machine tools to sophisticated acoustics. The evidence suggests that ancient Egypt possessed technical knowledge that we're still working to fully understand. None of this requires us to believe in aliens or lost super civilizations. It just requires us to take the physical evidence seriously and acknowledge that there are genuine mysteries still to solve. Ancient Egypt isn't just history. It's an ongoing investigation. Every new measurement, every new analysis, every new experiment brings us closer to understanding how they did it. And that's the exciting part. We're still learning. We're still discovering. We're still being surprised. If you enjoyed this deep dive into ancient Egyptian technology, make sure to subscribe to Pharaoh's Legacy. We've got more mysteries to explore, more evidence to examine, and more questions to ask. Hit that like button if this made you think differently about ancient capabilities. And drop a comment below. Which of these technologies surprised you most? What do you think is the explanation? In our next episode, we're going to explore the mystery of ancient Egyptian mathematics and astronomy. How did they calculate with such precision? What did they know about the cosmos? And why does the Great Pyramid encode mathematical constants that supposedly weren't discovered until millennia later? Until then, keep questioning, keep learning, and remember, the past is far more sophisticated than we often assume. This is Pharaoh's Legacy, where ancient mysteries meet modern investigation.